This webcast continues Activity 2 of the lab that is exploring how unbalanced net forces affect acceleration. In this part of Activity 2, we're doing the second experiment where we look at how acceleration depends on the value of the mass that is being accelerated. So in this experiment, the independent variable is the mass, measured in kilograms, and the dependent variable is acceleration, measured in meters per second squared. So in setting up this experiment, you need to reset your PhET simulation by clicking this orange reset button. Go back and click on the boxes for forces, sum of forces, values, masses, and acceleration. Very important, in this second experiment, set the friction to none. Move it all the way to the left so that there is no friction. Okay, I'm going to click this play button or pause button so that the simulation will only run when I tell it to run. And the instructions tell me to set the value of the applied force to 400 newtons and that the first value of mass is 50 kilograms, which is the mass of the crate alone. Okay, so I'm going to do that. I'm going to leave just the crate. I'm going to set a you might have to fine-tune it a little bit, set my force to 400 newtons, and I'm going to click the run button just for a couple of seconds and then pause it again. So the reason that we set the friction equal to none is because when there is no friction, the applied force and the sum of forces are the same. So the net force is equal to whatever force the orange man is applying. Okay, so for this 400 newtons of applied force on the 50 kilogram crate, the acceleration is 8 meters per second squared. And so I'm going to go and in table 3, here at step 34, I record the 50 kilogram mass and the acceleration. So then I want to find combinations of masses. So next I want 100 kilograms, and so for that I might want to just bring a second crate on top of the original crate. I'm leaving the applied force at 400 newtons all the time. I never change the applied force in this second experiment. I'm going to run it for a couple of seconds and pause. And with this combined mass of 100 kilograms, now my acceleration is only 4 meters per second squared. And so I would record that in my table. Okay? And so I'm going to keep building this table with all of these combinations of masses. And so, and then I'll record the acceleration. Once you've completed table 3, then you want to use Microsoft Excel to graph the acceleration versus mass. And so to do that, I'm just going to put my data from table 3 in Excel, and then I'm going to make a scatter plot. So I'll highlight my data and insert a scatter plot. And look at the shape of this. This is not linear, it's obviously curved, and because of the way it's curved, as the mass gets larger, the acceleration decreases, so they're moving in opposite directions of each other. That means this is an inverse function. Okay, so here's mass, and here's acceleration. And then we do need a title here, right? It would be acceleration versus mass. Okay, so this graph I would put in my lab report here at step 36. Okay, and the type of relationship is an is that it resembles an inverse function, which has the parent equation y equal some constant, it's represented by k, times the inverse of x. The inverse of x is 1 over x. Okay, so now I need to linearize this data, and the way that I'm going to do that is to take the inverse of the mass. Okay, so I'll go back to Excel and I'll show you how to put a formula in to do this. I'm going to copy that original table, just copy it and move it somewhere over to the right. But I'm going to delete the values of the masses because I'm going to make this the inverse of mass, which has the units of 1 divided by kilogram. Okay, I'm not changing the acceleration. I'm leaving that the same, right? I have not changed that at all, but I'm going to calculate the inverse of mass. Okay, so here's how you would create a formula in Excel to do that. You could also use your calculator and do it by hand if you want to, but I'm going to use a formula. So I click in the first row of this new table, and I'm starting my formula with an equal sign, and then I'm typing 1 divided by. I bring my cursor over here and I click on the first mass where that 50 is. When I click on the value of that first mass, it puts the cell address here in my formula, and then just say enter. Okay, and once I've got that formula in that cell, I can just drag that formula down, and so it will calculate the inverse of each one of the masses in my original table. Okay, so I've got that. Let's see what the graph of acceleration versus inverse of mass looks like. So I'm just inserting a scatter plot. Oh, look how beautifully linear it is. Okay, so remember this now, it's no longer mass on the x-axis, it's inverse of mass, and so the units are 1 over kilogram, and then of course acceleration is still our dependent variable. So this is acceleration versus the inverse of mass, and I would put that in my lab report here at step 39. Okay, and so now we have a linear graph, and so we would like to write the equation of this so that we will have a mathematical model that represents the data from our experiment. And so I need to run linear regression in Excel in order to get that slope. And so I'll go to, let's see, data analysis, and I'm going to run regression. Let's see. It has the old data from the first experiment, so let me just take that out. Okay, so on my y range, I want to put the acceleration because that is, what's on the y-axis of my graph. For the x range, I'm putting the inverse of mass. Make sure that you put check boxes for residual plots and line fit plots, and then say OK. And we have then, and I'm going to format those cells to auto-fit the column width, and here we go. Again, my line fit plot shows that my predicted y is a very good fit for the original data. My r-square value is very high, so this is a good fit. And the intercept is the y-intercept, the x variable 1, that is the slope that I'm looking for. And so I would put this linear regression in my lab report at step 40. And now I'm able to write a physics equation. So my independent variable now for this linearized graph is no longer mass. Now my independent variable is the inverse of mass, or 1 over mass is going to be the symbol I'm going to use for that. My dependent variable is still acceleration. Okay? The units of this slope are meters per second squared over 1 over kilogram. And so if I, instead of dividing by 1 over kilogram, that's the same thing as multiplying by kilogram. And so I get kilogram meters per second squared. Hey, that's just a Newton. A Newton is a kilogram meter per second squared. So then we have in step 43, some additional experiments were run using different values of net force. And so we see they're all, when we graphed acceleration versus inverse of mass, they're linearized. We're just going to put our data in that same table. And then we can talk about what the slope of the acceleration versus inverse of mass means. And basically, in every case, the slope of that linearized graph resembled the net force, right? Our slope was 400.18, but our net force was 400. So very much resembled the net force, and the units simplified to be units of newtons. That's the unit of a force. And so we conclude that that slope has a meaning, which is net force. So then I'm going to restate the physics equation from step 41, except now we are replacing the numerical value of the slope with what it means. It means net force, or sigma F. Okay? And so now we can state Newton's second law of motion. When the net force is non-zero, an object accelerates. The acceleration is always in the same direction as the net force. An object's acceleration is proportional to the net force acting on the object and inversely proportional to the object's mass.